Welcome, everyone, to the New Jersey Climate Change Resource Center Spring Climate Academy's webinar, Impacts of Climate Change on Coastal Forests. I'm Marjorie Kaplan. I'm both the Associate Director of Rutgers Climate Institute and along with my colleague, Jean Herb of the Blaustein School of Planning and Public Policy, I co-direct the New Jersey Climate Change Resource Center. I'm going to give you a few logistics. Today's webinar is going to last until 1. And other than today's presenters and our Rutgers team, you're all muted. So to communicate with us, please type your questions into the chat box, which I'm sure you're all familiar with. But just in case, look at the bottom of the screen. You'll see a little bubble. It says chat, and you can send us questions and comments. But please send your note to all panelists, as that ensures all of us working behind the scenes today will see your questions. I want to thank my colleagues, Matt Drews and Dr. Perry Ferraro here at Rutgers for their help with our webinar. And I want to let you know we're recording our webinar and it'll be available on the New Jersey Climate Change Resource Center website, which I believe Carrie will put into the chat box. So one continuing education credit is available through the Association of State Floodplain Management, and one certification maintenance credit has been requested through the American Planning Association. So please reach out to us after the webinar if you need a certificate. I'm really pleased about today's webinar because this is a project I have been involved in with my 3 wonderful collaborators. So let me tell you a little bit about them. Rachael Sacatelli is a research coordinator at the Center for Remote Sensing and Spatial Analysis here at Rutgers. Her work focuses on coastal problems, including the impact to coastal forests on climate change that we'll be discussing today. Rachael recently completed her master's at Rutgers in coastal ecology, and her thesis work focused on coastal forest dieback in New Jersey. Glen Carleton is a hydrologist for the New Jersey Water Science Center of the U.S. Geological Survey. Glen's main area of focus has been groundwater flow modeling, with particular emphasis on stormwater infiltration and groundwater mounding, flow and solute transport in fractured rock aquifers, and variable density saltwater intrusion modeling. Glen has worked at USGS for more than 30 years, and he has an MS in engineering geology and hydrology from Drexel University. And Rick Lathrop is professor in the Department of Ecology, Evolution, and Natural Resources at Rutgers. And Rick is also the Johnson Family Chair in Water Resources and Watershed Ecology at Rutgers University. Rick serves as director of the Walton Center for Remote Sensing and Spatial Analysis. His research program works to integrate insights of landscape ecology and geography with the application of geospatial information technology to improve our understanding of the structure and function of coupled human environmental systems. Working with partners, Dr. Lathrop attempts to translate that understanding into effective and appropriate techniques to improve on-the-ground natural resource management and land use planning. I'm going to remind you all to please put your question in the chat box to all panelists. And at the conclusion of this webinar, you're going to be provided with a link to a very brief survey about your experiences with the Climate Academy thus far. And that's going to help us to better understand your needs so that we can more effectively plan for future events. So now it's my pleasure to invite Rachael to join us. Rick, I believe, is going to share his screen. And they'll talk to you a little bit about this wonderful project, which I was lucky enough to collaborate with all 3 of my colleagues on today. So take it away, Rick and Rachael and Glen.
All right, hello everyone. Very happy to be giving this presentation today. Like Marjorie said, my name is Rachael. And I'm going to go over kind of a little bit of the introductory information and set you guys up to understand the problem that we are discussing today. And then I'll kind of get into showing you where and why those things are happening. So that's my part. And then after I kind of go through the problem, Glen will take over and start telling you guys more about the whys of our coastal dieback issue. And then Rick will come in and tell us a little bit more about what happens to the ecosystem after these events and some of the knowledge gaps and management implications for those impacts. So if you want to go to the next slide. This project on coastal forest dieback, which I'll define in a second, was to help the U.S. Forest Service in making decisions with respect to the coastal forests that are impacted by climate change. So we kind of wanted to get into it. They wanted to know what the state of the knowledge already was on this issue. Then they wanted to identify any of those key knowledge gaps and management approaches that Rick will talk about later today. So in order to do that, we conducted an extensive literature review, trying to get at all of that already completed research on these issues. And then after that, we had an interview with, or during that, we had an interviews with regional experts, and then also a workshop held in January of 2020, right before the pandemic. We got that nice and in. So to kind of get an idea of unpublished or kind of on the ground knowledge of what's going on in those ecosystems. And then our kind of next steps here is a more intensive mapping study of all the areas that that are being impacted along the coastline, which is kind of in the works as of right now. So for today, we're just going to kind of talk to you about what we already know, what we think we know, what we definitely need to know, and then what we can do about those things as far as we understand. So on the next slide, I will, so just in case anybody here isn't super familiar with what we're talking about when we say coastal forest ecosystem, these forests lie right next to the saltwater marshes in mostly the back bays of New Jersey. So Barnegat Bay ecosystems, and there's Hudson River ecosystems, and then there's Delaware Bay ecosystems, and they all kind of follow this interesting zonal pattern. So depending on how much water an area is getting during the tide, so whether or not they get flooded by the tides early on in the cycle, so right after low tide they start to get inundated with water in these marshes, versus the parts of the marsh that only get inundated during like high tide events or really high tide events. Depending on how much water they see on a daily or monthly basis, changes what plants live in that location. So we have like the lower marsh, which is the area that is often frequently flooded, the high marsh with different set of plants that gets flooded kind of occasionally. And then on the edge of that higher marsh area, we have the invasive Phragmites area. We have a very dense, especially in the mid-Atlantic, Phragmites problem. So there's lots of dense Phragmites right there that starts to transition into a more shrubbier area, and eventually right behind all of that is the coastal forest. So this is kind of the place that we're talking about, and what is happening because of climate change. Sea level is rising, and there's millions of reasons why this is happening, which we'll get into, which Glen will go into a little bit more detail on. But what has been noticed is, if you go to the next slide, the appearance of what we call ghost forests on the next slide. There we go. So ghost forests is what has the key term in the colloquial term for coastal forest dieback as a whole. So what happens is that we found large swaths of areas where forest used to be and is now turning into a more marsh ecosystem. It's termed ghost forest because you see these large dead trees. They don't fall often. So you have these dead twigs of trees still left on the marsh, and it does kind of look like the ghosts of forest past. And these ghost forests are popping up all along the region, the Mid-Atlantic Northeast region, to be specific. seeing it all the way from, Virginia, Maryland, North Carolina up to Massachusetts and kind of around that curve there where these types of ecosystems exist. So on the next slide. I'm going to get you a brief overview of the study that I did, just to kind of give you an idea of a little bit more context on what's been happening over the past 100 years or so, to make us think that this probably has something to do with sea level rise and climate change. So I did a kind of case study in New Jersey for my master's thesis, studying 8 different sites along the coast of New Jersey, and looking at it from an aerial point of view over a longer time frame. So if we go to the next slide, what I did, and hopefully these will play, is I found aerial photography, so photos taken from planes from 1940 all the way up to 2015, in spurts, because there's, can't go back in time and get more imagery. But I found those imagery, and I marked out on the imagery where the extent of the live trees, the forest edge, was in some of these ecosystems along the coast, and documented as time went by the shift in where the forest edge was over that 100 years or so time frame. So as you can see, these are 2 of the more extreme situations, but there are areas in New Jersey with large amounts of forest loss over that time period. And if you go to the next slide, we can see all of the sites that I did, kind of the 1940s tree line where it was in the 1940s, and now where it is in 2015. So 1940s is in yellow, and the 2015 tree line is in red. So as you can see, in just the 8 representative spots that I chose along the coastline, there's been large amounts of coastal dieback and large appearances of these ghost forests. So all of this area between the yellow line and the red line are either that ghost forest appearance with the dead standing trees, or have already completely turned into regular old, high marsh, low marsh, Phragmites dominated marsh. So to kind of quantify that, if you go to the next slide, I kind of got some numbers on that. So what is it? So the distance between these 2 lines, we're talking, because it's sometimes hard to see scale in these pictures, but we're talking from anywhere between an average of 28 meters of loss, linear distance between those 2 lines, all the way up to an average of 606 meters of forest loss. And that's in linear meters, distance from one line to the other. But we found areas where our maximum change was 784 meters of loss in some of these extremes. And because I have, a line in 1940 and a line in 2015, I can do some math and get a rate of movement. So how much did it move per year? And in the graph on the right, it shows how that's the meters per year of forest loss on those edges. So it goes anywhere from less than a meter to 9 meters a year. And that was definitely not consistent. There were definitely times where there were large spurts of dieback versus shorter spurts of dieback, but for the most part, those are the average rates of movement per year for each of those sites. And if we kind of look at that on a year-to-year basis on the next slide, we kind of see that, each one of these plots here, these box plots here, represents where the forest tree line was at that time. And if you notice that the rate of change are what those points are. So the rate of change over time in each interval, for the most part, obviously, save for a couple of outliers here and there, but for the most part, the rate of change over time is accelerating, as far as we can tell on the couple of sites that I did work on for New Jersey. There are a couple of sites that are, the rate of change is not increasing. There's one site where I found it's decreasing, and that raises the question of why are they so incredibly different site to site? Because even the ones that are increasing over time, those graphs are incredibly all over the place. If you look at the Delmont site right there, third from the top, you can see like large distant differences between year to year span. So it didn't die a lot in the 1961 to 1970, but then 1970 to 1978, there was lots of death that happened. So there's lots of different, it leads us to believe that there's lots of different reasons for why the death is occurring when it is. So if we go to the next slide, I just want to reiterate that this is not just, I just did work in New Jersey, but this is not just a New Jersey problem. This is an entire Northeastern coast problem that have these type of coastal forests, which is pretty much from North Carolina to Massachusetts, give or take. There's plenty of studies that we found in the report, which you can read at a later date if you're more interested. But here are two examples of a number of different of studies that happened in the past. There's one studying forest diving in the Chesapeake Bay, and then another study shows that in Maryland we're getting big changes in forest retreat rate over time. So forest retreat being this dieback. So in Maryland, in Virginia, in North Carolina, all of them have seen increased forest dieback over a number of years post industrial revolution. So on the same time scale as the sea level rise that we're often talking about, on that kind of large number, sea level rise has risen, 8 to 12 inches, depending on who you talk to, since the pre-industrial. So those kind of timescales are what we're talking about here. So to the point of this being a very complicated system, on the next slide, we came up with sorry. First, I'm just going to talk about to kind of to come up with what I'm going to talk about on the next slide, which is our concept map of what we think is going on in these systems. We got together. It wasn't just me, Rick, Glenn, and Marjorie who decided that this was what's going on. We researched all of those, all of the research that has happened in the past, and then we got together with all of the rest of the scientists. So we tried to get as many of the scientists working on this problem together that we could find or that were available to come and talk about their perspective on these issues and what they're seeing and why they think it's happening. And we took all of that information and kind of conglomerated it together to create this conceptual model of how we get from climate change to these changes in vegetation communities. So that why are these forests dying? And how are they being replaced? So going from climate change, there's two different places that this could be the change could be coming from the changes in storms that we see because of climate change and sea level rise, also caused by climate change, and a vast web of different pieces of those issues all boil down to these changes in community. And Glenn is going to go into more depth with some of these drivers as we get there. But when we talk about these mechanisms of change, we have our ultimate drivers, which is climate change and the changes in storms and the changes in sea level. And then kind of proximate mechanisms, which are things that happen because of climate change, which are kind of that first underlying reason for these changes that we're trying to kind of suss out. And this is an incredibly complex system. So it is highly likely that we're missing things here. It's highly likely that we need some more research, which is what Rick will go on to tell you about what we think we're missing at the end here. But it is also important to notice that there are pieces of kind of human-based factors that are also being, contributing to these issues. Things like our farming and the mosquito management, which we have historically done since the 30s, ditching large ditches to drain the marsh or putting in large ponds to allow for more fish to swim around and eat our mosquitoes. These things are all interacting with the system, the natural system, as it were, and either somehow influencing how the coastal forests are dying. I'm going to hand it off to Glenn to kind of go into more detail about all of these different drivers of forest dieback.
Okay, thank you, and I really want to thank Marjorie Kaplan for pulling into this, and it's been great working with her and Rick and Rachel. I'm the U.S. Geological Survey, and groundwater is my life, and with respect to living things, I don't know so much, but fortunately others do. So I'm going to just talk to you about the physical groundwater system. So this is just a brief outline of what I'm going to go over. I'm going to talk about just the hydrologic cycle, how the groundwater system is recharged by precipitation and discharges to streams and tidal waters. And we're going to talk about the effects of sea level rise and the different factors that are killing the trees. I'm grateful to be able to do this from home. Kat is here sitting next to me helping me because he just needs my company all the time now. And it's very not seeing an audience. I'm gonna try to be funny. That's my shtick, that's my bow tie, the whole thing. If my jokes seem inane, I apologize. I'm just doing my best. So the next slide. And I have you can hear me, but there's a bit of a delay on my end. So this is one of several different cross sections I'm going to show you, all done by different artists showing similar things. As I said, precipitation is recharging groundwater, so that's on the left side of the screen. Precipitation infiltrates down, hits the water table, and then it's going to flow over towards the coast and discharge to wetlands and directly to tidal water. And, it's not a uniform sandbox. There might be some clay layers in there. And off to the right is where salty water, and that purple section in between is a bit of a transition zone where it's not salt water and it's not for fresh water. And thank you, Rick, for showing with the cursor what I'm trying to say. So next slide. They say a picture's worth 1,000 words. I felt like I needed 31 extra words to describe groundwater flow concepts. So in this case, 1,031 words made. We have precipitation. Some of that precipitation will land on the land surface and immediately run off to streams and won't infiltrate at all. Some will infiltrate, but then be taken back up by the trees or evaporate directly. And we have a $1 word for that, evapotranspiration, because as I said, I'm a groundwater hydrologist, and I'm not going to distinguish between direct evaporation and transpiration by plants. I'm just going to say evapotranspiration. If it leaves the groundwater system, it's gone. I don't care about it anymore. So, whatever does not run off or evapotranspirate is left to infiltrate down to the water table, at which point it is my world. We're saying now it's recharged to the groundwater. And if you want to put that in an equation, recharge is equal to the precipitate minus the runoff minus the ET. Then the groundwater that recharges is going to flow towards a discharge point, and it's going to discharge to the nearest stream, or sometimes follows a long flow path and is going to discharge to a river or directly to tidal waters. Next slide. So this is a different cross section showing essentially the same thing. This happens to be on a barrier island, but you see the precipitation, you see the groundwater recharge. There's groundwater, in this case, discharging back from the water table up to the atmosphere from a wetland. And then again, we have down at the bottom, we have the saltwater, freshwater interface, which, we like to think of it as being a sharp line, but it's not. It's a, the real world has lots of shades of gray. So next slide. So this is one of 3 graphics that were done for us by the Department of Agriculture. This one is showing, so you have to rise, take 2060, and the third one with additional sea level rise in 2100. And the concept again here is that we've got recharge on the left side, groundwater is flowing towards the tidal waters, and you see that there's a inland low-lying area that currently is forested, and that's all fresh water there. If there's ever standing water after a hard rain, that's fresh water. It's above the water table, and groundwater is flowing towards the coast. We have that transition zone I described before. There's the salt marsh, and the salt marsh is actually often dependent on some of that fresh groundwater discharge. Some of the plants, and again, it's not my area, so I can't tell you which plants, but some of the plants, especially in my salt marsh, are dependent on fresh water. They can't take all salt water. So that groundwater discharge is an important part of the ecosystem, the fresh water coming into salty water. And the high marsh is going to be inundated only at high tide, and is that my area? I think there's areas that are inundated, at the spring tides, at the full moon and the new moon, but not inundated every tidal cycle. And then it goes on down to the low salt marsh that is inundated every tidal cycle. So when there's a storm surge, that salt marsh is used to that. It expects to be inundated from time to time. And you can even have trees like that sort of lime green tree, showing that's a stressed tree. It's totally healthy, but, it can handle the occasional storm surge. As long as the salt water is not there for too long, that tree will survive. Okay, next slide. So, again, I apologize because I can't see the next slide yet. I'm sure it's coming. So the effect of sea level rise on shallow groundwater is that if you have groundwater discharging to a stream well inland, then it's not affected by sea level rise because the elevation of the stream doesn't change. The groundwater is discharging to that stream. It's affected by the elevation of the stream. That's not changing. So the water table doesn't change. So that can be hundreds to thousands to more than thousands of feet inland. But the idea is that once you get a certain distance away from the coast, the groundwater system doesn't know that sea level is rising. However, a stream or a wetland that is closer to the coast is affected, and in that zone, the groundwater is going to rise at the same rate as the sea level rise. You know, they're just locked right together. And you can have a situation where trees that are adapted to living with a shallow water table, you know, 1 or 2 or 3 down, you know, 1.5 feet down, they can handle their roots being covered with water for weeks at a time, but not for months at a time. And when the water table rises because of sea level, that fresh water is coming up and will saturate the root for too many, you know, days per year. And it's going to, quote, I don't know that drown is a technical term here, but it's the way non-plant people like me can comprehend it. So a good example of this is the Hall Maritime Forest, particularly on Sandy Hook. It's one of the only 2 old growth holly forests in the country. And it's some of the trees are being stressed by sea level. So this slide is going to show you, I liked it better that way. Thank you, Rick. This slide, the red dots in the top half of the graph are showing sea level at the Sandy Hook gauge, at the Cape May gauge. And you see over time that sea level is going up, and on the side is 1960, the right side is 2020, so about 60 years. The blue dots are from groundwater levels measured in a well, pretty close to the coast, but a freshwater well. It's a shallow water table well, and the water in the well is fresh. But you can see the water table is going at the same slope. And so we just fit a line to that. And up at the top, I did a little math here. Y equals mx plus b, to remind you of your algebra from 8th grade, where m is the slope of the line. And the slope of the tide gauge, the red dot, is 4 times e minus, and the slope of the groundwater is also 4 times e to the minus. They are the exact same slope. So this is proving the point. And I just have to interject here. I was so excited when I saw this because I thought it was true, but it was really great to get real world data proving it was true. Okay, next slide. So this next slide is 2060. And so the water table has come up a little bit because sea level has risen a little bit. So in the center of the cross section, you see the word water table. And just below that is, perhaps you can't read it, but it says 2020 water table. So the water table has risen, and that tree on the right by the salt marsh that formerly was stressed is now dead. So that's a ghost forest because the sea level is inundating that marsh, and that tree that used to be just far enough inland and just far enough above, that tree is now dead. And even on the inland wetlands, you see there are more stressed trees shown by that different, lighter color green, and they're stressed by the water table coming up. There's no storm surge coming over that high hill in the middle, but the water table is rising. So we have trees that are being stressed both by fresh water from the water table rising and from salt water. All right, next slide. So I'm talking about the freshwater killing trees in the more inland wetlands, but probably the majority of ghost forests are created from saltwater. I just want to make the point, it's not necessarily only saltwater. So when the sea level rises, that freshwater saltwater interface that I've been talking about does rise, but it doesn't rise very much. It's not really a big deal. The much bigger deal is that low-lying land close to the coast is inundated by water, and that saltwater interface is moving in because the shoreline is moving in. And that's where you're going to get trees being killed by the salt. So farther inland, a wetland that's not getting inundated with saline water, it may just be fresh water. There's one other situation that can maybe is obvious, which is trees that are pretty far inland, but they're on a tidal estuary where you have water flowing down and salt water in the salt front that moves. And I wish I was in person. I'm going to gesture here on camera. Every tidal cycle, the saltwater front line moves up and then down with the tide. But as sea level rises, that's going to move farther inland. And so Atlantic white cedar trees that are adapted to living in very wet conditions, but in freshwater, they can be killed by the salt moving estuary. All right, next slide. So this one is, the third version of the same graphic. This is 2,100. And again, these aren't precise numbers. We're just trying to make the point that the sea level has continued to rise. It's inundating farther inland where the salt marsh was. So the salt marsh is moving inland, more trees close to the coast died. And we also have a ghost forest on the freshwater wetland because the water table has risen so much, it's killed trees that were not adapted to living in constantly wet, mangroves, red cedar, certain trees are able to handle very wet conditions. But if you remember the 2020 slide, the water table was a ways down. All right, next slide. So I'm just going to quickly go over this because I'm just really proud of this graphic, but it's really a bit much for this presentation. But the point I'm trying to make here is that we see blue and dark blue colors. The water table on Sandy Hook has come up essentially the same amount as sea level rise. So it's affected the whole water table, not just at the coast. And all of those red areas are places where the water table used to be below land surface in a low-lying area, and now the water table has come up. And this is with 0.6 meters of sea level rise, about 2 feet. Okay, next slide. So this one, it's the same graphic I showed you before. I just want to make a quick diversion into talking about drinking water, just to make sure we're talking about kind of different things. The groundwater system, the shallow groundwater system with respect to ghost forests. It's a shallow system, not necessarily where we're getting our drinking water from. And down at the bottom of the graph, we have a confined aquifer. So the green is a clay layer. Water doesn't flow through the clay very well. So the water in the confined aquifer is all fresh. See, even offshore, it's got fresh water. So my geology controls every aspect of your life. You just didn't realize it. The reason Atlantic City has been so successful is because there's fresh water 800 down, and around the turn of the last century, they had the equipment drill 800 feet down to fresh water, and that allowed all these giant hotels on that small island. So next slide. So the confined aquifers are not as affected by the sea level rise and the freshwater saltwater interface moving. And again, this is just a quick slide from our study of Sandy Hook, a USGS study of Sandy Hook. The red line underneath freshwater on the barrier island is where the salt interface has moved up a little bit. And you see on the margins right there where Rick's cursor is on the right side by the Atlantic Ocean and on the left side, it hasn't very much. So that's not affecting the plants. Up there where he is now with the cursor, on the left side in the salt marsh there, yeah, maybe that's from inundation. But on the right side, the sea level rise isn't really affecting the freshwater saltwater interface. It's only when the inundation does it. All right, next slide. So again, just to repeat myself, there's going to be a negligible effect on the freshwater saltwater interface. The shoreline is steep, and that's even more true in a confined aquifer. But this is really important. And this is the end of my presentation. One more slide is surface water intakes that are in estuaries or pumping wells that are next to estuaries that are currently getting fresh water from that tidal estuary. Remember, there's fresh water coming downstream. When the sea level rises, that freshwater saltwater interface is going to move way inland. Next slide. So that the gradient of the estuary is really low, and that freshwater saltwater interface is going to move a long way in. So this is a slide from the Delaware River Basin Commission, and they're estimating the if you can see in the center of the slide, there's a purple arrow pointing to a 0. That's where the saltwater freshwater interface came in drought of 1960s. And that caused a lot of concern because Philadelphia's water intake was only 18 miles farther up. And they were terrified with the salt front had come up so far. If it came up to the intake, Philadelphia wouldn't have fresh drinking water. They estimate 3 feet of sea level rise will move the interface as much as 8 miles farther upstream. So that's almost 3 miles per 1 foot of sea level rise. That's a lot. Okay, so that's also important with respect to ghost forest. The freshwater saltwater interface is going to move upstream, way upstream in these estuaries, and potentially affect forests that are adapted to living in freshwater next to the freshwater estuary. All right, so that's it for me. Thank you.
Okay, thanks, Glenn. I'll take over now. So just to reiterate some of the points that Glenn made, the idea that, it's that soil saturation. So the two of the key drivers is that raising the water table, affecting soil saturation, that then in turn affects a number, the tree species themselves. So trees can withstand a few days of freshwater flooding, but it affects their growth, their development, especially their regeneration, and then ultimately their survival. And, in that coastal forest fringe, we have upland tree species and then wetland tree species. So wetland or riparian are more tolerant of saturated soils and the resulting anoxic conditions. But again, very few can withstand extended soil inundation. Now, the picture I have here is, bald cypress, which we have at the northern limit in southern New Jersey. They're one of those that are most tolerant, but even there, they have special adaptations in terms of their needs to be able to provide oxygen. And it's those locations, there's the freshwater and then episodic saltwater flooding, saltwater inundation that can then, it's kind of like a 1-2 punch, that the gradual increase of soil saturation and then episodic saltwater inundation that can be especially detrimental to the trees. And so I just wanted to give an example of that here on the Jersey Shore. And so Glenn mentioned Atlantic white cedar wetlands. This is a white cedar swamp. And so even these trees, you can see that they're standing water, but the trees are found on hummocks that are often above the water. And they're very sensitive to saline conditions. And so this is an area, Caddis Island. And so we're going to focus on this area. This is showing the area that was inundated by Superstorm Sandy in the blue. So if we look at this, this is pre-Sandy, and this is an Atlantic white cedar swamp here. We can see dying cedar. So this is what Rachel talked about in terms of a ghost forest with Phragmites coming in. Superstorm Sandy inundated this area, and you can see how that following year it killed all the cedar. The cedar are scorched. It's showing up at this orange color. And then several years later, you can see it's all dead cedar. So this is, you've got cedar dying here in that more gradual, what Glenn was referred to. And then we had a situation where you could have this episodic where you had stormwater inundation extending further in. And killing the susceptible cedar. But you can see other tree species, pitch pine, did not succumb to the saltwater inundation. So what's it look like there today? If you go out there, you'll see dead cedars, Some shrubs have survived, and then in some cases, extensive Phragmites. So in terms of some of the key knowledge gaps, one of the things that really came up is the importance of earlier land use alterations in terms of either intensifying or ameliorating the mechanisms that are causing coastal forest dieback. And so ditches and dikes can play a large role here in terms of enhancing or helping to mitigate the effect of the sea level rise. And the extent to which tree dieback, as well as lack of regeneration observed, is, as Rachel mentioned, it's complex in terms of salt intolerance, freshwater flooding, combination of the two, and that these different mechanisms can vary very spatially as well as temporally. And individual tree species have different salinity and saturation physiological tolerances. And so a better understanding of that is needed. And then the role of Phragmites. It can serve to hinder forest regeneration as well as subsequent replacement of other marsh species. So limit the expansion of higher marsh species like patons or into the expanding marsh. In terms of some of the consensus of our January 2020 workshop, was the consensus of the expert was there's a lot of coastal forest management focused on protecting assisting salt marsh ecosystems, but comparatively less attention has been paid to, specifically in terms of the adjacent forest ecosystem. And, two main strategies were identified. One was, okay, let's try to maintain the existing forest wetland in place, or two, manage the forest that responds and retreats inland in response to sea level rise and marsh expansion. And really, depending on the management strategy, might be possible to manipulate either hydrology and or vegetation community composition, again, to help push in a desired direction, whether to assist or hinder the forest migration. Now, there are possibilities of engineered infrastructure to try to either slow that, especially in terms of storm surge. As Glenn said, there's less that you can do in terms of the groundwater table. That's just going to rise with sea level rise, but you might be able to reduce either some of the flux in terms of tidal flux and or tidal surge. So in some cases, there are techniques to control the amount of tidal water entering an area. But really that these techniques are very costly and would need to be designed and implemented at a scale broad enough to be effective and would require continued maintenance. There are possible, in terms of vegetation management, to either maintain the coastal forest in place or potentially to replace with species better adapted to the newer environmental conditions. So planting more salt tolerant or flood tolerant species, and or controlling Phragmites to reduce those competitive interactions. One problem is in terms of southern pine beetle and other pests may hasten tree dieback and further complicate forest vegetation management. Really, I think in the long run, any kind of short-term forest vegetation management may be a losing proposition. And so you might be able to do something in short term. In terms of longer term, in terms of these decadal changes, the sea level rise is inevitable. So rather than trying to protect the coastal forest in place, the emphasis should be shifted to ensuring more of a no net loss of coastal forests at a broader scale. And this means, strategic land conservation and acquisition or easements to ensure that we maintain this coastal forests in our coastal zone. And so this may mean helping to facilitate the movement of forests or the regeneration, regrowth, afforestation at the inland edge, as we lose forest at the seaward edge. So how big is this problem here in New Jersey, or potentially how big is it? We've done some modeling. We estimate between 35 to 70,000 acres dieback by 2050. That's approximately about 3% of New Jersey's forest area out of 2 million acres. And just to give you some handle on that, we are in the process right now of doing this analysis from the states of Virginia up through Massachusetts to understand the potential area and what areas might be hotspots for future coastal forest dieback. To help inform adaptation planning, we've developed a number of web accessible tools, mapping and decision support tools, njfloodmapper.org, which basically shows where some of these forest dieback areas potentially are as way of NJ Forest Adapt. And then finally, if you don't want to put on your waders and head into the coastal forest to experience this firsthand and get eaten up by mosquitoes and ticks, head into Madison Square Park this coming May 10th and through November. Noted artist Mai Lin as setting up an installation called The Ghost Forest. And these are actually Jersey cedar trees. Bob Williams helped in terms of harvest some of these trees that were going to be taken down anyway and brought in for this installation. So you can experience the Ghost Forest firsthand. So finally, we have our report, which is available on the Rutgers University website. And I want to acknowledge all the people that, in terms of the original funding sources and the U.S. Forest Service and the Northeast Climate Hub, as well as our interviewees and the number of regional experts that participated in the meetings, as well as the reviewers that gave us important critique and feedback on the report itself. And then finally, Kara, for some of the infographics that Glenn showed. So with that, I'm going to stop share and open it up.
Thank you. That was great. Thank you so much to Rachel, Glenn, and Rick for a great presentation. I'm going to invite Dr. Carrie Ferraro, who's been monitoring the chat, and she's going to open it up to some questions for you. Carrie, you there?
Yeah, thanks, Marjorie. And thank you so much, Rachel and Glenn and Rick, for such a wonderful presentation. You actually, through your presentations, answered a bunch of the questions that had come in over time, but we still have a few left, so I'll pose those to you now. Rachel, to start out with, there was some question about, a couple questions about some of the data that you showed. So in particular, there was a question about whether the differences on Little Egg and other lower loss sites were related to elevation or topography.
Yes, so the Little Egg site in particular, the marsh that is there and the transition to forest is very steep. So at the edge of the marsh, as it goes to forest, incredibly steep there. So we think that is what is causing that kind of slow movement or consistent movement, because there was still loss. It was just a lot smaller than some of the other places we were looking at. So yeah, definitely a topography thing there for sure.
Thank you. And I think, that kind of I'm sorry, did somebody else want to? No, just noise. Okay, sorry. And kind of following in on that, I think you answered the question a while about whether that might also be because it's better protected. So I'll move on to the next question, which was, how much does the slope of the watershed matter in terms of the danger of losing freshwater forests? Is it an important factor, as important factor as distance from shore? And I'll pose that to all of you. I'm sorry.
Yeah, so as Rachel alluded, where you have a steeper incline, there's going to be less effect. Where there was the greatest effect was in those low slope areas down, for instance, like in Delaware Bay Shore. So the lower the slope, it's going to, the water table is going to more be closer to the surface, and then in terms of the sea level rise. So it's definitely the lower slope areas in our coastal that are, and that's where it's going to extend the furthest more rapidly as compared to where you have steeper inclines, greater topography in adjacent to the coastal salt marsh.
And I will mention that also the lower the slope the area is, also makes them more susceptible to big things like shore breaches and things like that. When you have these low slope areas, they end up getting flooded, and then that flooding stays because it's lower slope. That one area that I showed, the squiggly one in Delmont, that one, most of that dieback happened after a big shoreline breach along the shoreline there. So definitely makes them more susceptible.
Thank you. We had a bunch of questions kind of related to the impacts of what happens to these forests. Sorry, and I know, Rick, you mentioned that there's still a lot of research that needs to be done, but some of what was asked was for example, do these ghost forests as they die contribute a significant amount of carbon into the atmosphere? And are there any benefits of these forests of these forests still being there?
Well, one is the forests help serve as buffers, and so they absorb storm surge, and because there's a lot of, in terms of the more biomass you have there that serves as kind of friction as a storm surge comes in, will slow that surge. The trees themselves sequester carbon, and in some ways, as Rachel mentioned, those trees are actually don't decay quickly, so they're keeping that in place. There's some interesting research looking at the implications of what's happening in a soil, and the soil is so important in terms of carbon sequestration, and so that becomes more complex because you have anoxic conditions, you got changing soil salinity that's changing bacterial decomposition, and so that it's more unclear and be very site specific in terms of what that implication might have in terms of is it releasing carbon or is it actually storing carbon.
Gary, I think we have time for one more question if these guys will hold on, even though we're just at time, but maybe they'll be willing to take one last question.
Hey, thanks, Marjorie. So our last question is for you, Glenn. And it's again kind of site specific, but it was, do you have a sense of how the Barnegat Bay Lagoon tidal exchange affects groundwater?
Short answer is whatever system is in place there isn't changing. I don't think the tides are changing dramatically. I think what's happening is that the average elevation of Barnegat Bay is slowly rising. And from a groundwater perspective, that's really what we're paying attention to, is the average water level. The daily cycles are not as significant. So sea level is rising just as fast in Barnegat Bay as it is on the coast.
Great. Thank you.
So much.
Thank you. And so on behalf of all of us at the Climate Change Resource Center, we want to once again thank Dr. Lathrop, Glen Carleton, Rachael Sacatelli for their wonderful presentations. And you can find the report on our website. As a reminder, as you leave today's webinar, you're going to get provided with a link to a very brief survey, less than 5 minutes, really, really brief. And we really hope you'll take a minute to help us more effectively plan for our events. And look for an announcement in your inbox or on our website about the next series. This concludes this Climate Academy series, but we will be developing more for later in the early summertime. So thank you all. This concludes our event.